Hey, I'm right back. This is the same day, totally. It's not 3 days later. All right, so we did 5. Let's look at continue on. There's like another thing we gotta do. So remember that eliminating the parameter is an aid to curve sketching. So if the parametric equation represents the path of a moving object, the graph alone is not sufficient to describe the object's motion. You still need the parametric equation to tell you the position, direction, and speed at a given time. I'm honestly like just reading this. I'm not even listening to myself. Okay. Let's represent this equation by using the parameters t is equal to x, and then use the parameter m is equal to dy dx. So let's see what happens. So we've got the equation. Also notice this paper doesn't have lines on it. I hated the sound when I was listening back of me turning the page. Also, I've recently realized that when I clear my voice in videos, it's super loud. I'm sorry. Thank you for your patience. Okay, so we have this. So what we need to do is we need to figure out an x equation and a y equation. Oh wait, x is equal to t. All right, now we just have to make a y is equal to some t stuff. Oh wait, x is wait. This is literally, so y is equal to t minus t squared. Wow, so this would be our parametric equations. Literally just substituting in. Now this says m is equal to dy dx. So let's see what happens here. So I'm trying to get y is equal to x minus x squared into two different equations, one where it's y equals and one where it's x equals. And I have m is equal to dy dx. So let's find dy dx. dy dx is equal to 1 minus 2x, right, when we take the derivative of that. So that means that 1 minus 2x is equal to m. So one equation, remember, we want to end up with x equals something and y equals something. So I can say 1 minus 2x is equal to m. So let's back up. Let me explain how I got that just in case. So solve this for x. And then you plug it back in to solve for y. That's the short version. So the explanation of what's going on here. So it says m is equal to dy dx. I don't have dy dx. Here's my, like, this is my original, right? Y is equal to x minus x squared. I don't have dy dx. Oh wait, I have y equals stuff. I could take the derivative. So dy dx is equal to, I took the derivative. So this right here is dy dx, as well as dy dx is dy dx. And both of those things are equal to m. And so if my end goal is to say x equals some stuff and y equals some stuff, well, I could take 1 minus 2x and set that equal to m. Now I could actually solve this and get x is equal to some stuff. And I wish it was a t, but it's an m, and that's okay. So here's the thing. I'm dividing by a negative 2, so I'm gonna do this trick where you factor a -1 out of the top and then cancel the negatives. I think that looks a little bit nicer. Personal preference, either way would be right. So now I'm trying to get a y equals, oh, wait, I know that y is equal to x minus x squared, right? So I have x in terms of my parameter. Now I can get y in terms of my parameter simply by substituting, right? Because we know that x minus x squared is what y is, and we also know that x is 1 minus m over 2. There you go. Now I have a set of equations. I have an x equation and a y equation, both governed by the parameter. The no, okay. So then you got some fun pictures down here. Our calculator can do these pictures, and be careful The heck, where's my calculator? These are a rabbit trail where you can lose a good chunk of time when you mean to be paying attention and getting things done. So if we go in and we make a parametric graph, so if you make sine t, and then like it doesn't really matter, it's gonna, oh, let me see. Let's go out to, let's go from negative 10 pi to 10 pi. I'm having fun right now, by the way. This is not part of the lesson proper. This is like just trying to show you some things. So if you're trying to get done stuff as fast as possible, see you later. But what I just did was I said x is equal to cosine. Cosine's an oscillating value, right? I could make sine equal to an oscillating, oh, I said sine there. That's fine. What if I made this equal to sine? So what's happening is sine is going between -1 and 1, right? It's bouncing back and forth between -1 and 1. So our x-coordinate's bouncing back and forth between -1 and 1, and our y-coordinate's bouncing back and forth between -1 and 1. And so our graph is going to turn into this thing that bounces back and forth. The cool thing is when you make it, like let's have this one go twice as fast as that one. So, and also since I know sine never goes outside of 1, I'm just going to have this graph go from -1 to 1 in all 4 directions. So now my x-coordinate's going twice as fast as my y-coordinate, and that's fun. What if I have them go like, instead of one's going twice as fast as the other, what if that one's going like 2 and that one's going 3? That's a fun shape. What if that one's going 7 times as fast and that one's going 3 times as fast? Okay, so when I get these jagged edges here, it's because it's taking, the leaps it's taking are too great. So I'm gonna make my t-step smaller. So now it's just plugging in more points. Wait, why are you so far away? What happened? Where'd you go? Okay. That looks like an error down there. How did it get outside of 1? Oh, it like traveled back on itself. Oh, let me show you another cool thing you can do. If you go to y equals and move your cursor over to highlight that thing over here, and you click enter, it cycles through some options. This one, it's a little ball that follows the end. So for a parametric graph, it's actually really useful to see where it's going. So we'll see on this one where I thought it was broken. This is the kind of thing I would do with you guys in class, so I just wanted to show you. So it like reverses. Wild stuff, wild stuff. All right, let me up this again. So these are some fun things you can do, and like you can change it around though. Like what if you did tangent and then let's just keep them as both t's, what happens? It's gone. Oh, whoa. So, you know, tangent flies off to infinity at some point. So the really, really cool stuff, though, is going to come in when we do polar graphing. But they give you some cool graphs down here to try. And if you have that, the little ball on the end, it's fun to watch and see how it travels. So, yeah. We're going to learn about polar graphing next, after we do some calculus with parametrics. Don't worry, calculus with parametrics is, it's not hard, it's just we needed to learn what parametrics were. So we'll do that next, then we'll do some polar stuff, then we'll do some vector stuff. These are just like 3 separate ways that we do calc, like or three separate like categories of doing calculus. And it's pretty repetitious, honestly, even though the things are wildly different. And then we get to start sequences and series, which I can't wait. All right, I hope this was helpful. Yeah, Thanks for your patience through all this stuff, guys. Bye.